purpose of this video is to give you some general information about conic sections. You'll need the handout called Slicing the Cone. Your homework is to fill in the notes as you listen to the video and turn that in to me tomorrow. The first thing we're going to look at is how these cones, or how these conic sections come about. So first of all, you could fill in the curves produced when a plane intersects a double cone are called conic sections because they are sections of a cone. And I have some drawings to illustrate this, but I want to show you something that's a little more dynamic that would explain it and show it a little better. So I have here online a plane and a double cone, and we can kind of tilt this to show you that this is two hollow cones tip to tip, and we have a plane intersecting the cone at right angles to the axis of the cone, which goes straight down the middle of the cone like that. Now, if we tilt this cone, you will see that when we have a plane that cuts perpendicular to the axis of the cone, it forms a circle. Now, if I tilt this plane a little bit, then if I look inside, we see that it forms an ellipse. And the more I tilt it, the more elongated the ellipse becomes. Now, tilting this back again, if we continue to tilt this plane so that it becomes parallel to the edge of the cone here, so if we look at the edge, there's the edge of the cone, and this plane's perpendicular to that edge, or parallel to that edge, I'm sorry, I think I said perpendicular, this forms a parabola. So we have a parabola. Now, if we continue to tilt the plane so that it cuts through both what are called napes or naps of the cone, if I tilt this down, you'll see it forms the fourth conic section, which is a hyperbola. I want you to know something about the hyperbola. Notice that it is not nearly as curved as a parabola. It's almost V-shaped, as a matter of fact. Not exactly. Now, if I kept moving this until it intersects the vertex of the cone, you can see that instead of a hyperbola, it's not quite there yet. Instead of a hyperbola, I end up actually with just a pair of crossed lines, and this is known as a degenerate conic. So these are our conic sections. Pretty cool little thing, isn't it, to play with? So there's our circle, ellipse, parabola, hyperbola. So you can fill in then the name of the figure produced. Obviously here we have a circle, ellipse, parabola, and hyperbola. So those are the four conic sections. Now, when a plane intersects the vertex of the double cones, the intersection is either a point, which is what we have here, a line, or two cross lines. And these are all known as degenerate conics. Degenerate conics. So they're not actually a circle, ellipse, parabola, or hyperbola. And by the way, and just to let you know, this is not an eclipse. That has a C in it. It's an ellipse. Okay. The next thing I want to talk about is that each of the conic sections can be defined as a set of points that satisfies certain conditions. The most obvious one you learned earliest, is what a circle is. A circle is a set of points. I'm going to call this point P, and we're going to have, it has coordinates x, y. A set of points that are all equidistant, which just means equally far from, equidistance from the center of the circle. Okay, so every point that P is the radius r, that's the same from every, you know what I'm saying, never mind. Okay, ellipse. An ellipse, though, has 2 points here called foci. They're called F1 and F2. And if we have some point on the ellipse right here that is connected to the two foci, what's true about all of the points on the ellipse is that if we measure the distance from the point to each of the foci, add those two distances, the sum will always be the same. So I will define this, the set of the points for which the sum of the distances from the point to the two foci is constant. The sum of the distances from the point to the two foci is constant. And in fact, those two distances, and I'm going to call them D1 and D2 to correspond to what we did in the notes, D1 plus D2 is equal to the width of the ellipse. And actually, and technically, we should say the major axis, because if the ellipse was taller than it was wide, we might consider that the height of the ellipse, but it's equal to the longest part of the ellipse. The hyperbola is the set of points. Well, let me go ahead and just label this. I'm going to change these to D so they match what we did in the notes, or what we're about to do in the notes, D1 and D2. If we take some point and draw a line to each of the foci, if we take the difference of those two distances, it will always be a constant. So the set of points for which the difference in the distances from a point to the two foci is constant. And in fact, if we connect the two vertices here, this distance is the absolute value of D1 minus D2. And that's called the that's the transverse axis, the length of the transverse axis. Now, parabola, if we look at what we have in the parabola here, is we have a focus here, and we have what's called a directrix, which is a dotted line that is, we can think of the parabola as kind of sitting on. The distance from the focus and the distance to the directrix are equal. Those are equal distances. I probably should draw that better. Let me try that again. So the distance to the focus and the distance to the directrix are both equal. Those are the same distance. It turns out that no matter what point we put on here, I could put one over here, the distance from the focus to the point and the point to the directrix, if we drop a perpendicular line down to the directrix, is always equal. So these two distances are always the same. So the set of the points which are equidistant, in other words, equally far from the focus and the directrix. Now, these definitions then lead to the algebraic representation of these different conic sections. We're going to look specifically at the circle because it's the easiest one to do, and then I'm going to show you the parabola in the notes. We probably won't derive the formulas for the ellipse and the hyperbola, but it's done in a very similar way. So with a circle, let's just kind of sketch our circle. We've got a circle with center, and we're going to put the center at the origin because this is the easiest. Actually, no. We're going to put the center at a point HK. So let me redraw that. Sorry about that for you drawing your notes. So here's a circle. So we're just going to say here's our X and here's our Y and our axes. The center is at HK, and we're going to put a point here, P, and call that the coordinates of that X and Y. And we're going to call this distance R for the radius of the circle. What we know is if we were to find the distance between these 2 points, the distance formula tells us that the distance between points HK and XY is X minus H squared plus Y minus K squared. And we know that that distance is R. And all we have to do now is square both sides of this equation. If we square both sides of the equation, we get X minus H squared plus Y minus K squared is equal to R squared, which is the equation of a circle. with a center at HK. We can do similar things, as I said, for the other conic sections, but I'm not going to do that right now using distance formula. The other ones are a little more complicated. Okay, next thing I want to talk about conic sections is they can all be written in the form ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, where a, b, c, d, e, and f are all constants. Some of them could be 0, which means some of those terms could be missing, but they can all be written in general in that form. For example, if I had some sort of, let me just do an example for the circle. Let's say this is x minus 3 squared plus y plus 1 squared equals 3 squared. So I could multiply this out and say this is x squared minus 6x plus 9 plus y squared plus 2y plus 1 equals 9. Actually, I better change. No, that's right. That'll work. So this, I can write then that x squared plus y squared minus 6x plus 2y, and then I have 10 over there, 9 plus 1 equals 0. So notice I don't have an xy term in this one, but I can write it in the form ax squared with a being 1 plus 0xy plus 1y squared minus 6x plus 2y plus 1 equals 0. So this is the general form, and this is what's known as standard form for graphing. So let's take a look. Notice then we have different equations for these. We have 4 different equations here, one of which is an ellipse, a hyperbola, a parabola, and a circle. So how do we recognize them from their equations? The key things to look at are the squared terms. So if we look at the squared terms, here, 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 and here, how do we tell which one is which? Well, first of all, if there's only one squared term, it's a parabola. Only one squared term. Okay, second, we have if both the terms, the squared terms, have the same coefficient. So here we have a 4, both of them are positive 4. And that is a circle. Though the next one, 4x plus 9y, squared terms are different, but have the same sign. So they're both positive in this case. That is an ellipse. You can think of that as a circle that instead of being stretched out the same amount in each direction, it's stretched out longer in one direction than it is the other. So you have different coefficients. The hyperbola is the one where one squared term is positive and one is negative. And I'm not sure I'm going to fit that in, so I'm going to do what you can't do and move that down a little bit. And one is negative. That is a hyperbola. Now I want to call your attention, negative. Hyperbola, not negative. That one wouldn't have been worth a half point anyway. Okay, this is only true if b is 0. In other words, there's no xy term in the equation. If there's an xy term, if b is not equal to 0, there is an xy term. The conic is rotated, and these rules don't apply. So in other words, we can't recognize, if there's an xy term, we aren't going to be able to recognize the equation of a particular conic using the rules that we just described. But we'll talk more about that later. Okay, standard form of equation for conics. Now these should look familiar if you've had conic sections in Algebra 2. So when we look at this, we have here an x squared term and a y squared term. So it's not a parabola because we have 2 squared terms. Notice they are both, if we were to multiply this out, x and y would both be positive. However, we have two different numbers underneath. So this turns out to be an ellipse because unless a and b are equal to each other, so I'm going to specifically say a not equal to b. If a and b are not equal to each other, this is an ellipse. Now, the only difference between these two equations is I switch the a and the b. In an ellipse, by definition, we say that a is the bigger number, and so this would have the bigger direction going in the x direction. This one would have the bigger direction in the y direction. Okay, the second one, you notice we have two squared terms. We have the a and b underneath, but we have a subtraction sign. So here we have a positive x and a negative y. Here we have a positive y and a negative x. One positive squared term, one negative squared term. This is a hyperbola. The next one we have, hopefully you recognize that form of it. That's the circle that we just found up in the top of the sheet, this side of the page. Notice that if I divided everything by r squared, it looks very much like the equation of an ellipse. However, the only difference is instead of a and b being different numbers, these are the same numbers. So if you have an ellipse where the two numbers underneath are the same, it's really a circle. So a circle is just sort of a special case of an ellipse. Then the last one, you notice we have 1 squared. Here's an x squared term. The x is a squared term, but the y is not. And here the y is a squared term, but the x is not. So that's a parabola, only one squared term. Now, notice we have two types of equations. We have the general form of the equation up here, and then we have the standard form or the graphing form of the equation down here. Obviously, we're going to be learning more about how to graph these using the standard form of the equation. And it's often helpful to get from the general form into the standard form for graphing purposes. We'll be doing that by doing an algebraic process called the completing the square, which I'm sure many of you remember with fondness from Algebra 2. That'll be on the next video. Woohoo!